Greetings and welcome to Precalculus, a series on lectures of graphs and functions. We are going to focus on a library of different functions. All right, we're going to run through several different types of functions. The first one we're going to look at is a linear function. This just, when graphed, makes a line. You have probably seen this function before in the form of y equals mx plus b. Well, since we are using function notation, we're going to use f of x. So f of x equals mx plus b, where m and b are real numbers. And if m is 0, we get f of x equals b, which is a constant function. If m is 1 and b is 0, then the function turns out to be f of x equals 1 times x plus 0, in other words, x, which is the identity function. M generally will stand for the slope, and b will be the y-intercept. The domain of a linear function is negative infinity to positive infinity, and as long as we're not dealing with this constant function, the range is also negative infinity to positive infinity. If we are dealing with this constant function, then the range is just that constant. So let's take a look at some of these guys. When the slope is positive, it's going to go upward. So if I'm looking at this from the left to the right, it looks like I go uphill. If m is less than 0, meaning it's a negative number, then the slope is downward. From left to right, it goes downward. If our slope is 0, then it's the constant function, and it is a horizontal line at the value b. B could be positive, b could be 0, or b could be negative. And the identity function is when our slope is 1 and our b value is 0. And it is the line that goes right through the origin. You'll go up 1 over 1, up 1 over 1, up 1 over 1. All right. Now let's get to writing the linear function. So we're given that g of 1 equals 4 and g of negative 3 equals negative 2. We want to find the linear function. Now keep in mind, the function at x equals the output value of y. You can think of it like that. So this is 0.14. This is negative 3, negative 2. So let's take a look at the solution. We are looking for the function g of x in the format of y equals mx plus b. We need to find m, and we need to find the b value. So our first step is we need to find m. We have 2 points. We have the g of 1 and we have the g of negative 3. Those are 2 points. Our slope formula is y2 minus y1 all over x2 minus x1. Well, let's figure out that information. For g of 1 equals 4, our 1 is our x1, our 4 is our y1. For g of negative 3 equals negative 2, our x2 is negative 3 and our y2 is negative 2. Plugging in these values into our slope formula, we're going to get m equals negative 2 minus 4 all over negative 3 minus 1. All right. And negative 2 minus 4 is negative 6. Negative 3 minus 1 is negative 4. We can reduce this fraction down to positive 3/2. We have found our slope. Now that we have our slope, we can use the point slope formula to find the equation of the line. So here we go. Second step. Point slope formula is y minus y1 equals m times x minus x1. We know what y1 is. It's 4. We know what x1 is. It's 1. And we know what our slope is. 3/2. Let's plug in those values. And we get y minus 4 equals 3/2 times x minus 1. Let's go ahead and distribute this 3/2 through. And we get y minus 4 equals 3 halves x minus 3 halves. Now I'm trying to get it to say y equals something, so I have to get rid of this minus 4. Let's go ahead and do the opposite of minus, and we're going to add 4 to both sides. Because I'm adding a whole number and a fraction, I am going to have to convert my whole number over to a fraction. So 4 can be rewritten as 8 over 2. So we have negative 3 halves plus 8 halves is 5 halves. So this negative 3 halves plus 4 is really 5 halves. Now we have our equation. And we're just going to rewrite it in terms of g of x equals 3 halves x plus 5 halves. Now we can go ahead and graph this. I'm just going to use the 2 points that we were given. We were given 1, 4 and negative 3, 2, and connect the dots. Now to double check myself that I did all my work correct, my slope is positive. I better have a positive sloping line. Let's take a look at another example. We're going to determine the length of a megatooth shark. Now, we have a tooth from a megatooth shark, and we have decided that this total height of this megatooth specimen is 15.6 centimeters. We can calculate the length of the shark is going to be 0.96 times this height of the tooth minus 0.22. This is our formula we're going to plug in our values. Now the only value we don't know in our formula is right here, the height of the tooth, and we can get it from the problem set. So let's go ahead and throw this value in. And even though the tooth is measured in centimeters, our answer is actually measured in meters. So whatever we get out is actually going to be, let's say our answer is 10. It's going to be in meters, not centimeters. And we do not have to convert this. It's just part of the formula. All right, here we go. Our shark length is the 0.96 times the height of our tooth minus 0.22. Let's throw in this 15.6 from our problem right here for the height of the tooth. We get 0.96 times 15.6 is 14.976 minus the 0.22. We get 14.756. Now I'm going to approximate this. This is about 14.8. And remember, we're in meters. So this shark, this tooth, came from a shark that's approximately 14.8 meters. Now that is about 48.6 feet. Pretty big shark. Now let's talk about the square function and the square root function and the cube root function. The square root function is for every non-negative real number. There is only one principal square root, and we're going to denote it by the square root symbol and x as our radicand. Therefore, the equation y equals square root x defines the square root function. You may have seen this once before in your life too. Now keep in mind, it's for every non-negative number. That means our domain is limited to all values 0 and greater. So it includes 0, because I'm allowed to take the square root of 0, all the way up through all positive numbers. My range is also going to be positive. So you put in a positive value, it's going to pop out a positive. So from 0, including 0, all the way to infinity. Now here's an example. We're going to graph this square root function. And what I'm going to do is I'm going to do it two different ways. I'm going to longhand graph it, and then I'm going to grab my graphing calculator and graph it that way as well, so you can see what I'm doing. All right, the first method, let's try graphing this by hand. Now I'm going to be kind of clever about the values that I select for x. I do know my domain is 0 and all positive real numbers. So I'm going to choose an x, I'm going to throw it into my function, and I'm going to see what pops out. And I am going to write it as a point so it's easier to graph. All right, plugging in a 0 for x, I get the square root of 0 is 0. So the point I'm going to plot is 0, 0. I'm going to throw in a 1. and I take the square root of 1 and I get 1, and my point I'm going to plot is 1, 1. Now I could put a 2 in here and get the square root of 2, which is 1 point, well, let's see, the square root of 2, and it's 1.412, 4142, but that's a little hard to plot. So what I'm going to do is I'm going to try and be clever about the x values that I'm going to put in there. And so I'm going to use perfect squares. So the next value I'm going to use is 4. The square root of 4 is 2, and therefore I'll plot 4, 2. Next perfect square is going to be 9. So the square root of 9 is 3. So 9, 3 will be the point I plot. And I'll just do a couple more. 16, the square root of 16 is 4. Therefore, I'll plot 16 and 4. And the last point, I'll plot 25. The square root of 25 is 5. So I'm going to plot 25, 5. Now, this should give me a good idea of what the shape is. And I have already graphed this. And it looks like this. Here's my plot 0, 0. Here's my point 1, 1. Here's my point 4, 2. 9, 3, 4, 16, or 16, 4, and 25, 5. So it starts off very strong and then it starts to curve. That is our square root function. That's one way of doing this by hand. Now, let's see what it would be like to plug this into our calculator and let our calculator plot it. So first of all, I'm going to clear that. And let's see if I can get a little closer. Okay. See if we can focus. Okay. So what I'm going to do is I'm going to hit y equals, and I'm going to put in my function second square root, and I'm just going to put an x as my variable. It's my window size that determines what x values I'm going to use. So I'm going to go ahead and change my window. My minimum is 0. My max could be 30. It could be, let's see, let's go with 36 because 6 times 6 is 36. I'll do it in a scale of 1 is fine. Y minimum, I'm not going to have any negative y's, but I do like my graph to sit up above the bottom line just a little bit. So I'm going to leave it as -1. And my y max, it looks like I should go up to, I don't know, 7. I might not need it that much, but we'll see. And I'll also do the y scale of 1. And now I'm going to hit graph. Aha! Just like my hand drawn. It looks pretty good. Very similar. Okay, that is the square function. Let's take a peek at, let me get that out of the way. Let's take a peek, if I get my finger out of the way there. Okay, let's take a peek at the cube root function. Now the cube root function, there's only one cube root for every real number, but we are allowed to take the cube root of a negative number. So the domain is all real numbers and the range is all real numbers. It is f of x, or y equals the cube root of x. That's our function right there. I don't care if you call it y, f of x. I'm probably going to stick with f of x. And again, we have two different ways of graphing this. One is by hand. The other is going to be via my calculator. So let's go ahead and take a look. I am allowed negatives and positives, negatives and positives. So graphing this, I'm going to select some values. Again, I want to be, I don't want to say slightly clever about it, but I want good numbers popping out that I can actually graph. So I'm going to use -8 because the cube root of -8 is -2, because -2 times -2 times -2 is my -8. So the point I'm going to use is -8, 2. Next one, -1. Cube root of -1 is -1. So the point I'm going to plot is -1, -1. 0. Cube root of 0 is 0. And therefore I'm going to plot 0, 0. 1. Cube root of 1 is 1. And therefore 1, 1 will be the point I plot. And I might as well use 8. The cube root of 8 is 2. And therefore I'm going to plot 8, 2. And once I graph this, this is a smooth image. It is going to look like this. There's my 0, 0, my 1, 1, -1, -1, 8, 2, -8, -2. It is a very smooth curve. Second way of graphing it, using the calculator. All right, so I'm going to go ahead and I'm going to leave this guy here. I'm going to see what happens if I leave it here. All right, let's try and, there we go. Let's go to our second graph, and this time I want the cube root. Where is my little doohickey here? I am looking for it. I know I have a little symbol for it. I don't know. Here's my square root. I'm looking for my cube root. So I think what I'm going to do is I'm going to change this to a power and see if I can do it as a power instead of, usually they have a square root like that with a little x on it, and I can say what version I want. And I am not seeing it. Yeah, I'm just not seeing it. So I'm not going to fight the system. I am going to throw in the same version but using exponents, and that's going to be x to the 1/3 is a cube root. But I am allowed, this isn't going to be red, the square root is going to be in blue. I do still want to see my negatives, right? So I do have negatives, and right now my x is not set up to accept negatives. So I'm going to go ahead and say, all right, well, let's do it to 36. My y max, let's see, I'm going to do 5. I probably don't need it that big. And my y min will do -5 as well. So let's see what happens when I graph this. I'm hoping that that first graph, I can keep it in there so you can see the difference between the two. Yeah, it doesn't like it. So I'm going to kill that first one. I'm going to delete that one. And now I'm going to graph it. All right. Let's go with delete, delete, delete. That one's cleared out. That one's x to the cube root. And hopefully, yeah, it just doesn't like it. Oh, because my min and max are the same thing. That was dumb. Let's do -36. Now it should graph it. All right, -36. Let's graph. Woo, yay, we figured it out. All right, very similar to what I graphed. That's our graph of our cube function. Okay, our cube function. And we can change it just slightly. I don't need all of those little markers. There we go. Now it's a little bit cleaner. Same graph, just a little bit cleaner looking. All right. Pretty much for the rest of the lecture, I'm going to be talking about piecewise functions. What a piecewise function is, it has different rules which assigns the outputs depending on where you are in the domain. So let's take a look at what a piecewise function looks like. Okay, here we have our function f of x. And when you're in the domain that is less than 1, then you're going to use the function fx squared. If your value is greater than or equal to 1, you will use the function 2x plus 1. So let's say you have a value of 0. Well, that's less than 1. You would use x squared. If you have the value of 3, well, 3 is greater than or equal to 1, and therefore you would use the function 2x plus 1. So let's go ahead and evaluate using this function f of x, f of 0, and f of 2. Now we know 0 is less than 1, so we better use the first function. Let's throw that in there. F of 0 is 0 squared. 0 squared is 0. Now let's take a peek at f of 2. F of 2 is greater than 1, and therefore we will use the second function. We will evaluate it using f of x equals 2x plus 1. Now, let's throw in the 2. 2 times 2 plus 1. 2 times 2 is 4. 4 plus 1 is 5. So depending on what values we use is going to depend on which function we use. So let's take another example. Let's find and evaluate this piecewise function. Okay, in Peach County, Georgia, a section of the highway has a speed limit of 55 miles per hour. If you were caught speeding between 56 and 74 miles per hour, your fine is $50 plus $3 for every mile per hour over 55. If you're for 75 miles per hour and higher, your fine is $150 plus $5 for every mile per hour over 75 miles per hour. So it's two pieces. One is if you're driving 56 to 74 miles per hour, and the second piece is if you're driving 75 miles per hour or over. All right, so let's create our piecewise function that calculates our fine. Then we're going to figure out, well, what's the fine if we're driving 60 miles per hour? And what's the fine if we're driving 90 miles per hour, assuming we get caught? Okay, now we have two setups. One is going to be when x is when our miles per hour that we're driving is between 56 and 74 miles per hour. And then the second piece of the function is going to be when we are driving 75 miles per hour or more. Okay, let's let x be the speed at which we were ticketed. That's the speed we were driving. If you're driving anywhere between 56 miles per hour and 74 miles per hour, then we have a fine of $50 plus $3 times the miles per hour over 55. So our function is going to be 50 plus 3 times x minus 55. This will give us the miles per hour at which we were driving over 55. So for example, if we were driving 60 miles per hour, that's 5 miles over the 55 limit. If we were driving 70, then it's 70 minus 55 is 15 miles per hour over the speed limit. So that's our first function. Second function, anytime that we're driving 75 miles per hour or higher, this fine is now $150 plus 5 times however many miles per hour over the 75 we were going. So very similar to the first one, 150 plus 5 times x minus 75. So here's our two functions. F of x will be 50 plus 3 times 5 minus 55 if our x value, the speed at which we were ticketed, is anywhere between 56 is less than or equal to x is less than or equal to 74. Okay. The second one is 150 plus 5 times x minus 75. And that's for if we were driving 75 miles or over. So 70 miles per hour, 75 miles per hour or more. So that's x is greater than or equal to 75. Now we want to figure out, well, what is our fine when we're driving 60 miles per hour? So we need to find f of 60. Since f of 60 is in between 56 and 74, we're going to use the first function, 50 plus 3 times x minus 55. Plugging in 60 here, we get 50 plus 3 times 5. Well, 3 times 5 is 15, and 50 plus 15 is 65, and therefore our fine is $65. Let's figure out what our fine will be if we're driving 90 miles per hour. Since 90 is greater than or equal to 75, we're going to use the 150 plus 5 times x minus 75. We're going to plug in our x, which is 90. We get 90 minus 75 is 15. 5 times 15 is 75, and 150 plus 75 is $225. But you got to catch us. I mean, we're going 90. So you got to catch us before we have to pay the bill, right? Tickets. Okay, let's take another look at a piecewise function. Sometimes we're just given the points. So here's our points. 1, the time is 1, the value is 1. Time is 3, the value is 5, the time is 5, the value is 2. We plot the points, and then we connect them in which the order we were given them. So this point is 1, 1, this point is 3, 5, and this point is 5, 2, and we connect them in this order. As you can see that there is a line going in this direction, and there's a line going in this direction. That means we have two functions. This is not just one line. Lines do not break in the middle and go a different direction. Because of that, we're going to have to figure out the equation of the first line and then the equation of the second line. Okay, piece 1 of the puzzle is the line going from 1, 1 to 3, 5. That's going to be our first line that we solve for. The second piece goes from 3, 5 to 5, 2. That's the second line we're going to solve for. When you're thinking about this, I have 2 points. How do I solve for a function when I'm given 2 points? First step, figure out slope. Second, use the slope in one of the points to figure out your equation. We'll do this not once, but twice. Okay, let's find the equation for piece number 1, which is the 2 points, 1, 1, and 3, 5. First step, find the slope, then next use the point slope to find the equation. Our first slope equation is y2 minus y1 all over x2 minus x1. Our first point, 1, 1, our x1 is 1, our y1 is 1. Second point, 3, 5, our x2 is 3, our y2 is 5. I'm going to plug these values into our equation, and we will get 5 minus 1 over 3 over 1, minus 1. 5 minus 1 is 4. 3 minus 1 is 2, and 4 divided by 2 is 2. So we now know our slope is 2. And it doesn't hurt to go back to the image and make sure that that slope in the first piece is positive. Good, because our slope we calculated is also positive. Next, we take the slope in one of these points. It doesn't matter. I'm just going to stick with the x1, y1 that I have listed. And our point slope is y minus y1 equals m times x minus x1. Plugging in our m of 2, plugging in our x1 of 1, and our y1 of 1, we get y minus 1 equals 2 times x minus 1. Let's go ahead and distribute this 2. We get y minus 1 equals 2x minus 2. Add the 1 to each side so we can get everything off of the side and we can get it to say y equals. And we get y equals 2x minus 1. That is our equation of the first piece of the puzzle right there. But this piece of the puzzle is only good when x is less than or equal to 1 all the way up to 3, including 3. All right? So 1 is greater than or equal to x is greater than or equal to 3. I'm only allowed to go up to 3 for this one. The second piece of the puzzle are the same exact steps, except we have 2 different points. So I'm going to use this as my first point and my second point. Slope, y2 minus y1 all over x2 minus x1. Our x1 is 3, our y1 is 5, our x2 is 5, our y2 is 2. Plugging on all these values into our equation in the right places, we get our slope equals 2 minus 5 all over 5 minus 3. 2 minus 5 is negative 3. 2 minus 3 is 2. And therefore our slope is negative 3/2. Now going back to look at the picture, does it make sense to have a negative number? It sure does, because that is a negative slope. All right, next, use the slope and one of the points. I'll just go ahead and use the 3, 5 point to figure out the equation of the line. Using point slope, I get y minus y1 equals m times x minus x1. Plugging in my y1, my m, and my x1, I get 5, y minus 5 equals negative 3/2 times x minus 3. I'm going to distribute this negative 3/2, and I get y minus 5 equals negative 3/2 x plus 9/2, because a negative times a negative is positive. I want to move this 5 over, so I'm going to add 5. But because a whole number and fraction, I need to have the same denominator. This is going to be 9/2 plus 5, but I'm going to convert this 9/2, and I'm going to convert it over to, I should say the 5, I'm going to convert it over to 10/2. 9/2 plus 10/2 is 19/2. And therefore the second piece of the puzzle is the equation y equals negative 3/2 x plus 9/2. So for the second piece, f of x equals negative 3/2 x plus 19/2 for all values 3 is less than or equal to x is less than or equal to 5. Okay. Now we have the 2 parts and pieces. We know the domain for each piece. Now we're going to put it together in a piecewise function. F of x now equals 2x minus 1 if 1 is less than or equal to x is less than or equal to 3. Negative 3/2 x plus 19 over 2 if 3 is less than x is less than or equal to 5. Now, I don't care if you would have put an equal here, like less than or equal to, but just so we don't have any overlap, either don't put the equal here and put it here, or put it here like I have, in terms of 1 is less than or equal to x is less than or equal to 3, and don't put it on the second function, just so there's no, I don't want to say overlap. It's okay to have overlap, but it's just clear that if you have a 3, you'll use the first one versus, oh my God, I have a 3, what do I do for both of them? Okay, decide where you want to put that 3. Okay, graphing piecewise functions, you're going to consider this function. It is a piecewise function. F of x equals the absolute value of x. You are going to use negative x if your x value is less than or equal to 0. You are going to use x if x is greater than or equal to 0. Those are 2 things that you're going to use. For any negative value, x will use the negative x. For any positive x, you will use f of x equals x. Okay, now let's go ahead and graph this. I know I'm going to use the function negative x for all negative values. So here we go. For a negative 1, I will use negative 1, which is positive 1. For negative 2, negative 2 is positive 2. Negative 3, negative 3 is positive 3, and negative 4, negative 4 is positive 4. So it looks like a line piece from 0, not quite 0. There should be an open dot here because I'm not including 0, but I'm going all the way down there, out to as far negative on the x and positive on the y that I can get. The second piece of the graph is going to be, well, for all positive values including 0, it is that value. So, for example, 1, it is 1. 2 is 2, 3 is 3, 0 is 0. So we are including 0, 0 this time. Now, to graph the whole entire absolute value piecewise function, both of these are going to go on the graph. So both parts on the same graph. So this is your first part, this is your second part, and therefore that is the absolute value function. It is a piecewise function. Let's try another piecewise function. This time our function is defined as negative 2x plus 1 if x is less than 1, and 3x plus 1 if x is greater than or equal to 1. Now, the only way that we can do this is you could try and throw it into a calculator, or you can say, you know what, I'm just going to try some values of x and try and figure it out. So that's what I'm going to do. I'm going to try a list of values for x and see what comes out of it. I'm going to choose negative 3. Well, negative 3 is less than 1, so I need to use this function of negative 2x plus 1. So negative 2 times negative 3 plus 1 is 6 plus 1, which is 7. Next, negative 2. Well, again, negative 2 is less than 1, so I'll use the first function. And I get negative 2 times negative 2 plus 1 equals 4 plus 1 is 5. Negative 1. Again, negative 1 is less than 1, so I'll go ahead and use the first one. I just want enough points to where I can plot this. So negative 2 times negative 1 is 2. 2 plus 1 is 3. 0. 0 is still less than 1, so I'm still going to use the first one. Negative 2 times 0 plus 1, well, 0 plus 1 is 1. 1. 1 is not less than 1. It equals 1, and therefore I'm going to use the second piece of the function, 3x plus 1. 3 times 1 is 1. 3 plus 1, 3 times 1 is 1 plus 1. 3 plus 1 is 4. And I'm going to do it a couple more times. 2, again, 2 is greater than 1, so I'm going to use the second. 3 times 2 plus 1 is 6 plus 1 is 7. And 3. Again, 3 is greater than 1, so I'm going to use the second one. 3 times 3 is 9. 9 plus 1 is 10. And there we go. And I'm going to plot each one of these. All right. So if I was to do the first piece of the puzzle, which is everything up until we hit 1, but we don't include 1. So we don't include 1 on the x. That's why it's an open dot. But then we graph all the rest of it. So we have a line looking like that. If I was just to graph the second function, it would look like this. So x is greater than or equal to 1. So starting at 1 and moving up, I've plotted a few points and connected the dots in a straight line. But we do not graph them separately. We graph them on one graph, and therefore our final answer is the line including the open dot for the first part of the function. Then we jump up and plot the rest of the function. This is a perfect example of a piecewise function. Two pieces of the puzzle. You can graph them separately, but ultimately you have to bring them together. All right, let's talk about one more function. Some piecewise functions are also called step functions. There is a step function that we do use frequently, which is called the greatest integer function. It's denoted by a double bracket with your function inside, or it's also called int parenthesis x. If I was going to graph this on the calculator, I would use int x. When we're writing it in paper or typing it up, we usually use these double brackets. And that just means, well, whatever value's in here, we're going to take the greatest integer less than or equal to that value that's in there. So let me give you an example. If our greatest integer function for 2, well, is 2, because 2 is an integer. The greatest integer function for 2.3 is 2, because I didn't make it up to 3 yet. That would be the next integer. 2.7, the greatest integer, is also 2. We are not rounding, so this is not because it's 0.5 we round up. We are looking at the biggest integer that's involved, and you could pretty much, on all positive numbers, just cover the decimal, and that's the greatest integer. Likewise, with the greatest integer of 2.99, again, cover up the decimal when it's a positive number, and you will get what the greatest number integer is. Sometimes it's easier to see it on a number line. So here we go. 2. 2.3 is right here. You can see I didn't make it all the way up to 3 yet, so the biggest integer is still the 2. 2.7 is about here. I didn't make it up to 3 yet, so I have to slide back down to 2 to be the biggest integer that I've seen. I'm traveling along. I'm 2.99. The biggest integer I've seen so far is 2. I haven't reached 3 yet. Now, positive numbers are pretty easy. You just chop off the decimal, and that's the integer you get. Some of the confusion is when we have negative numbers. Sometimes that causes issues. So let's take a look at this. -2, and we want the biggest integer. It is -2. -1.9, the biggest integer we've seen so far is -2. And you're probably going, what? Okay, just hang with me. -1.1, the greatest integer, is -2. That doesn't make any sense, right? Hold on. I'll show you on a number line, and it will hopefully make sense. -1.001, the greatest integer is still -2. Here's the reason why. This dot is traveling along the negative number line, and it lands on -2, and that is the largest integer it has seen along its journey. This integer is -1.9, and it has traveled along the way. It saw -2, and then it stopped. It didn't see any other integers. Think of it like that. Now, -1.1 is right here. And it traveled its journey all along the number line. It saw -2, hello, -2, and then it keeps traveling. That's not an integer, that's not an integer, that's not an integer, and it stopped. The only integer it saw was -2 along its path. This is -1.0001. And again, traveling along its journey, it sees -2, says hello, and keeps its journey. It sees some decimal and decimal and decimal and nearly sees the next integer, but it didn't get there. It is right before it, and therefore it has not seen the -1 yet, and therefore its greatest integer is -2. Now, if I would have said, what's the greatest integer of -0.9? Well, -0.9 is right here. Its greatest integer is -1 because that's the last negative integer it saw along its journey. So for positive values, you can just cut off the decimal. Don't do any rounding. Just cut off the decimal when it's the greatest integer function. When it's a negative, you're going to have to roll back to the previous whole negative integer that it saw. Right? So if it is a -1 and then some, you got to go back to -2. -1 and then some, go back to -2. -1 and then some, go back to -2. -0.9, okay, the last its integer saw was a -1. I know it's a little weird, it's a little tricky, but just think about making a journey along a number line and what was the last integer that value saw. When we're graphing a value like a step function, for example, our greatest integer, here's what we're going to get. I'm not going to write this as I go. So if your value is anywhere between -2 is less than or equal to x is less than -1. Remember, we can go all the way up to -1, but as soon as it is -1, it's no longer that value. Then, okay, between these, we're going to be that line. So any x between, here is -2, including -2, all the way to -1, but don't include -1. That's going to be our output. Any value, and it should be, that should be -2. And that should be -1. So -1 all the way including, or not including 0, but all the way up to 0. For 0 is less than or equal to x is less than 1, it's going to be 0. But not including 1. It's this step function. Okay, so here we go. Here we go. That's if it was 2. Here's 3. It stays 3 all the way to the next value, but it doesn't include it. Once it hits that next value, it jumps up to the next value and goes through. All right, that is the greatest integer function. It's called a step function because it steps and then jumps up, jumps up, jumps up. All right, that is it for this lecture. Until next time, be seeing you.